So it's a great pleasure for me to introduce Professor Laurent Younes from the Department of Applied Mathematics and Statistics at Johns Hopkins. He's the current director of the Center for Imaging Science and a member of MINDS and of the Institute of Computational Medicine. He was chair from 2014 to 2020, I think. Is currently associate editor of the Annals of Applied Statistics and former associate editor of Pattern Recognition Letters, Journal Imaging, Mathematical Imaging and Vision, IEEE Transactions in Image Processing. He's author of a famous book on shape and diffeomorphism, recommended to read for those which are interested in the topic, and is a great expert in differential geometry, machine learning, statistical methods for shape analysis, medical imaging. So Yes, supervisor of many students and postdoc. He does very interesting work in the field, so we are very grateful to have him in the seminar series. Please, Dr. Younes. You might be muted.
So thank you to Alessandro and Kathleen for inviting me today and giving me this opportunity. So I wanted, you may have noticed that I changed the title at the last minute so that it matches the one which is in the announcement, but don't worry, it's exactly the same talk. So this comes from a paper co-written with Nicolas Charand at JHU. So what I'd like to do in the hour, and we'll see how much I can cover from this plan, is just giving a quick introduction to what we mean by Riemannian shape spaces, and so motivating a little bit the construction that will come, and then discuss methods that will first try to introduce some elasticity concept in these shape spaces with all the caveats that will come from the fact that we want to have Riemannian metrics, and then see how we can also include a growth tensor and try to cover a little bit of everything. But so let me start first with motivating a little bit the construction of shape spaces. And so of course shape, and especially in biology, is a fundamental concept. It's been used to essentially justify several points in evolution theory, or of course it's the main subject of Darcy Hanson's treatise on growth and form. But the efforts for building a mathematical model of a shape space is maybe a little more recent. I think the first Riemannian shape space that I know of came from David Kendall's paper on a Riemannian metric defined on shapes represented as a collection of labeled points. And this construction has been very successful and are still used by a lot of users in a lot of applications right now. So the method is, well, we use you consider the sub collections of points, so it's n points in some dimension, and they are labeled, so ordered, and you put a Euclidean metric on them, and then you remove all the invariants that make a collection of points a shape. And these invariants in Kendall shape space is rotation, translation, and scaling. That can be some variation on that. And then you end up with a Riemannian manifold, and on this Riemannian manifold you can you can define, you can apply some statistical methods, and that has been really employed by many users since Kendall published his shape space paper. One of the limitations is that, well, this is ordered point that requires labeling. This is just points, nothing, no continuous object. And so since the construction of these shape spaces, a lot of effort has been devoted to remove the labeling assumptions and, more importantly, deal with objects such as curves or surfaces. But the approach has been mostly the same. You have a big space on which you define a relatively simple norm, so a banner space or a Fresher space, depending on so Fresher wouldn't have a norm, but okay. For example, you can represent a surface as a space of immersions from a manifold to RD. And once you have this structure, which is well known, some infinite dimensional space, you quotient out everything you want to quotient out. And there's the additional thing compared to Kendall's version of shape space that comes from the fact that we are dealing with continuous object, which is that we want to quotient out reparametrization. So the general notion, the continuous notion of relabeling. And so there has been a lot of work on that with a lot of, I mean, some new things that happened. Even the pattern is the same compared to Kendall shape space. The first one is that there is not that many choices that could have been made for a norm in finite dimensions. In infinite dimension, there are a lot, and what you find as the final shape space depends a lot of the norm that you chose in before quotienting out reparametrization and other transformations. So this is an important aspect, and I wanted just to mention these efforts because this is a big part of what people refer as shape space. I wanted to start with this. Actually, this is not exactly the construction that I will use in this framework. It will be slightly different, and the construction I will use is coming from diffeomorphic action. So this is maybe a second approach for building shape spaces. You know that the diffeomorphism group of RD can affect arbitrary subsets of RD, so in particular shapes and surfaces, shapes or curves, or I mean curves and surfaces, and they can transform almost any shape into any other, provided you don't change the topology. But and so what you can do is that given a metric in the group of diffeomorphisms, you can define an alignment method between two shapes by trying to find the diffeomorphism closest to the identity that transforms the first shape into the other. And of course, the construction will depend on the metric. But if you build the metric properly, you will also end up with a metric in shape space. So this is what we want to discuss as a first example. So I just want to mention that this is rooted in first Darcy Thompson's models and in Grenander's metric pattern theory. And this is very flexible. There has been a lot of applications that I will definitely not talk much about of this approach that led to what is called the large deformation diffeomorphic metric mapping algorithm, or LDDMM. I will say a few words on that. I want just a slide that just say that there are many other ways to address shapes not that many that build shape spaces. And I'm really focused on shape spaces here. Okay, so one of the limitations, or maybe a feature, I don't know, of these shape spaces is, well, they are based purely on geometry. So when people design shape spaces, they didn't have any biology in mind, or even any physics in mind. And this is natural because we are just looking at shapes that are not part of any natural process. If we are comparing a hand to another hand, there's nothing, I mean, at least the hand of one person to the hand of another person, there's no natural process that defines the transition between them. And there's no reason to say that, well, the deformation should be elastic, for example. But when we consider, so I mean, the advantage of that, well, I will go back on that, is that, well, that gives us a lot of freedom to modeling, and so we can take whatever is convenient to us. Now, if you look at actually biological process such as growth, then you cannot ignore the fact that there is something happening beside the geometry, some physics or chemistry, and so far there hasn't been a lot of effort in shape space to take this into account. So this talk is going to partially try to address this issue. So before that, I need to give some notation and some definition associated with this LDDMM shape space, so the diffeomorphic action shape space. So now we want to fix some notation. So the shapes will be modeled as embeddings from some manifold M into RD. Typically, it's going to be the unit sphere for things that are sphere-like. And if it's in 2D, would be the unit circle, because we like to deal with curves that are mostly like more or less like Jordan curves. So the notation is, when we have embeddings that we are going to call MP of M for these embeddings, provided they have P continuous derivatives, and each element in the set of embeddings is a shape equipped with a parameterization, so the equivalent of a labeled shape, because for every point on M, I have labeled a point in RD through the embedding. And so we are interested in shapes modulo parameterization, which means that you to apply on the right a diffeomorphism on the set of parameters without changing the shape. And so we get a quotient space, a space of equivalent classes that we can call M with a bracket around. Now the second part of the model, so this is our shape space. The second part of the model is the group of diffeomorphisms. So we take the group of functions that are from RD to RD, which are one-to-one smooth CP, invertible with a smooth inverse. And we based on that forms a group, and we are, so in here we are going to call the diff P or diff 0 if the diffeomorphism goes to infinity, to the identity at infinity. So if you have a diffeomorphism and a shape, you can combine them by an embedding. Sorry, you can combine them by applying the diffeomorphism on the left, so just moving the points on the shape, and because the parameterization is acting on the right, there is no problem. You can also, this action also passes to the quotient when you apply reparameterization. So this is an action on shape spaces. And so now to compare two embeddings or two shapes, we look at all the transformation that maps one to the other, and we decide that two shapes are similar if there is some transformation that relates them and is close to the identity. And so to define this, we need to define a metric on the diffeomorphism group, and that's what we want to do next. So to define metrics, you essentially have to define the length or the energy of paths in a set. So here, that means that we have to consider time-dependent diffeomorphisms or diffeomorphic motions. Not sure it's a great term. And so when you have something like this, you can measure the derivative with respect to time. That gives what is called the Lagrangian velocity. Or if you compose this Lagrangian velocity with the inverse transformation, you get the Eulerian velocity, which characterizes the deformation through the ODE that is, I don't know what I have to as a pointer, but I don't know if you probably see my mouse. And so the arrow, I mean, you have this ODE that defines, although to reconstruct the diffeomorphic motion using the Eulerian velocity. And in the model that we are making something that corresponds to right invariance, and that says that the kinetic energy associated with the metric only depends on V, but not on phi. So it doesn't depend on the transformation that has been applied up to time t, which is a fluid mechanics assumption rather than an elasticity assumption. So to define this kinetic energy, we need to define a norm associated to Eulerian velocities. And so for this norm, we need some space for this Eulerian velocity. So we consider a Hilbert space of vector field on RD that we call V, and we define the kinetic energy as the integrated kinetic energy, or the action functional, as the integral of the norm of the Eulerian velocity over time squared. And that defines the length of, the action of a diffeomorphic motion, and geodesics, so minimizing length curves, are those that minimize this action with fixed boundary condition at the initial and final times. So this builds a metric on diffeomorphisms. That's the full definition of the metric. This is just repeating what I said. So we minimize the action functional with fixed boundary conditions. Now, this metric can be applied to a shape space. So mostly the last equation defines a metric between shapes through trying to find the diffeomorphism closest to the identity that transform one shape into another one. And so that gives us a second variational problem that defines the distance in shape spaces that minimize the same action functional, given that the velocity transport the shape m0 over time. So this is the equation here, to a shape m of 1 that is consistent with the target shape. And this is a typo here. It should be m1 in D. And so we get a different problem. These problems can be interpreted as optimal control problems when the state is the shape and the control is the velocity. And just one more point, when we solve this optimal control problem in practice, it's very difficult to solve the exact problem that is given here, where you want to exactly transform a shape into a target shape, and we just relax the fixed endpoint condition by a cost whose design is very important, but for which I will not have time to give any detail. But that provides the LDDMM problem. Just one point is that the function u that we use in practice are based on embeddings of shapes into a much larger space on which we have a norm. And so we call that a chordal metric. And there's a bunch of metrics that have been defined associated with these embeddings. Okay, so one example simply of LDDMM evolution. Here it is. Oops, giving it again. So this is just one curve becoming another, just to have one image at some point in the presentation. All right, so what do we get with this? We get nice properties of the metric. So remember that we were pretty free of the model that we could done. There was no physics that we had to be faithful to. And so if we embed our Hilbert space V that defines the norm in spaces of vector field with enough derivatives, we get all nice properties that we want to find. There exist minimizing geodesics. There are solutions of the geodesic equation. We can also use for implementation the reproducing kernel of V that I will have to come back to that in later. And for example, the metric space associated with the distance is a complete metric space. However, as I said earlier, we want to do a little more and have something that is a little more has a little more physical or biological plausibility, and in particular, what we're going to talk about is how we can combine this LDDMM model with a model that includes some elasticity. We don't want to give up the LDDMM model, and we won't give it up because it provides all these nice properties that I just listed that are not shared, for example, by elasticity. But we want to introduce some concept that modify the metric into what we will call an elastic metric, which is actually, we will see not exactly something related with exactly elasticity, but inspired from it. So let's first remark that the model that we had before had a kinetic energy that only depended on a Hilbert space V. Every part of LDDMM would have been would still be satisfied if instead of depending on a given Hilbert space, this metric would depend on a shape at a given time. So that would create an optimal control problem in which the running cost depends on both control and shape. And so it's well behaved and provides a Riemannian metric in shape space with some reasonable hypothesis. The way we are going to apply this is to replace the norm of V, the norm on V, by adding something that depends on the deformed shape that will relate to elasticity theory. And so we are going to use a norm that we can call a hybrid norm, which is given in this equation, in which there is one part which is the previous norm that we had, that is independent of the shape, and this other part which depends on the shape but doesn't have the nice properties that ensure existence of geodesics, etc., that we have for LDDMM, but just the first component is going to provide what we need anyway. So I'm just going to discuss the 3D case in the construction of these shapes, maybe show some examples of images. Alessandro, are you raising your hand?
Yeah, so I was wondering, so the Euler-Lagrange equation of that variational problem are gonna still be semi-linear with that norm, correct?
Excuse me, semi?
The Euler-Lagrange equation that you obtain are gonna still be semi-linear with that norm. Is that correct?
What do you mean by semi-linear?
Semi-linear, I mean that the nonlinear part is gonna be in the not as a coefficient of the highest order derivative.
Well, but in any case, the even, I mean, the Euler-Lagrange equation is not linear. And
Right,
it's,
but the nonlinearity doesn't appear. So the highest order derivative has coefficients which do not depend on other derivatives with that norm. Is that correct?
I'm not sure. It's actually not even a differential equation. It's an integral differential equation. So
You're right.
I'm not sure that I'm trying to have one example of equation in mind. I think the higher level term is quadratic, but it's still, because it's a conservation equation, it still has solutions. Yeah, I need to we can talk at some point about what the equation is. It's called the Euler-Arnold equation. I'm not sure it's linear. So the so I'm just repeating here that something which is well known about elasticity is that, by the way, I see only 4 windows in the on my screen. If anyone has a question, just interrupt me. No need to raise your hand. Just talk. So the if you have a hyperelastic material, the energy is typically defined in this form with elasticity, where G depends on dphi transpose dphi minus the identity, and which is I mean, dphi transpose dphi is the Cauchy-Green tensor. So this is elasticity, and then there are all a lot of things that can be said on this. But what is important is that G is a function of X and a symmetric matrix. And I shouldn't have said positive semi-definite. Sorry about that, but because it's because I removed the identity. But what I'm interested in is not something that is a measure of energy associated with a diffeomorphism. I'm trying to look at something that would give me a norm on Eulerian velocities, which should be therefore first order approximation of this energy. And so if you do this first order approximation, you find that this is something that gives you linear elasticity. You find that this is something that depends with respect to what would be our Eulerian velocity. Something that is a positive semi-definite bilinear form on the set of symmetric matrices, and this is applied to dv plus dv transpose, or dv plus dv transpose over 2 if we prefer. And so that this is what we use. This is just this first order approximation so the linear elasticity that we'll use in defining what we will call elastic metric. And just skipping these details, this elastic metric will be associated to a shape which is in special case is neither a curve nor a surface, is just a volume. So it's even simpler. And so we have, oops, we are going to define a hybrid metric like we did before, with a part that is associated with the Hilbert norm V and some part that depends on the deformed object, which in that case is a volume in 3D. And just to define this metric, we apply what we had before. And so all this second derivative of with respect to W that I had before, I'm calling that capital B. And as often done, the dV plus dV transpose over 2, we call it epsilon. This is the infinitesimal strength tensor of the deformation. And B can be, at this level, any positive semi-definite quadratic form on the set of symmetric matrices. And so if you just count, that means that there are 21 parameters that are available to B. If you do the usual thing in elasticity and try to remove invariances, like Euclidean invariance, etc., you get back without any surprise to known models such as the Saint-Venant-Kirchhoff material that is just defined by its Lamé coefficient. So this gives, what I'm interested in here is that this gives me an expression that depends on V, a quadratic form that depends on V, or Eulerian velocity. And so this expression is just going to, as written here, be the extra term that will complete the norm in this hybrid model. So we apply this in a situation a little simpler, a little more complicated than the isotropic material described by the Saint-Venant-Kirchhoff energy, but I will not have the time to get into these details. Simply saying that we were trying to model materials that has layers, a little bit like the brain has layers, and trying to use models that were essentially isotropic along layers and non-isotropic across layers. Let me, so it's just to say that we end up with a model which is slightly more complicated than the one we had before, on which we did some experiments. You can do exactly the same approach on surfaces, and here really I do not have the time to give the details, but it's exactly the same idea. It's just use the principle of using elastic material, try to, do a first order expansion, use some invariance condition, and what you get at the end is a model for deforming surfaces that has 15 free parameters. If you want some isotropy, you reduce it to 4, three parameters, and you get an elastic energy. I just want to show you. So I hope it's going to work. Yes, I have a video, not a video, sorry. And there's a typo here. It's so the first one, and so that's the typo is really not helpful because this is so let me show you. This is a deformation that doesn't have the elastic term. And you can see, so this was taking the initial shape directly to the target one. It's very good approximation of the target shape. But what you can see is that the optimal deformation is creating this cluster of points, which makes the estimated parameterization, the optimal parameterization formed by LDDMM, not very uniform. And if you do it with an elastic term, this is a typo, you get something a little, still a very good approximation, still a very good approximation of the target, same quality, but better behaved. Okay, so you could do this with curve, and I'm going to skip this. That's a curve deforming. And so I have now, I mean, in the last 15 minutes that are left, I want to talk a little bit about how you can go further and incorporate growth in your model. So still trying to remain in this shape space framework in which we want to be elastic metric, except that we are going to remove that at some point later on. But at least from some part, we want to have an elastic metric that incorporates some notion associated with growth. So we're going to borrow from morphoelasticity, in which the typical way to model growth is through what is called a growth tensor, capital G, that explain for part of the Jacobian transformation of the differential of the diffeomorphic motion, and where the other part is subject to some elastic energy. And the only thing is that if we linearize this becomes very trivial, because this capital G in the product just becomes an additive term in the derivative of the vector field, the Eulerian velocity. And so this is just here decomposing the derivative of the Eulerian velocity as a term that model growth plus a complement that making the derivative of something. And so if we put that back in our elasticity model, we had dV minus dV transpose. I mean, we should put here A plus A transpose. And so it's dV plus dV transpose minus G plus G transpose. And we're going to assume that G is symmetric, so that we will just have minus G. And so in this expression, we are first going to try to minimize the this term with respect to both dV and G. This, in general, is not trivial. There's this condition, I forgot the name, that it's called the curl condition or something like that, that is needed for the minimum of this expression in B to be 0. So we get something that is still there's still something to minimize. And so we are going to replace the previous hybrid model that we had, and it is given here, which was just adding an elasticity term to the original norm by a model which is optimizing over growth, the elasticity term, and we get a new norm on V. So one can study this model and can prove some properties. So far, we only have theoretical result about that. We haven't implemented the search for geodesics using this model, but it's an interesting model that at least keeps the notion of a Riemannian metric by incorporating something that model grows, and somehow it tries to model a deformation by a shape change by trying to find the optimal growth combined with the optimal motion. So I'm going to skip the results associated with this, but I want to also say that we could model growth as something that can be interpreted as a force, and so that requires me to introduce two operators, the duality operator over Hilbert space. So they are those that, I mean, KH in particular is the operator that is associated with Ries's theorem that takes a linear form and transforms it into a vector in a Hilbert space. And so in addition to this, we have this bilinear form B, which can also be modeled as something that comes from an operator, which is the elastic operator, and this operator is called beta, and so if we define here, I mean, we will use the notation in which beta is integrated over a domain. And with all this notation, you can end up by identifying the action functional or the energy associated with our growth model by something you need. It's just a little algebra that is applied here, and if you so if you want to minimize this energy with fixed g, you find that the optimal vector field has to take that form. And I cannot linger too much on the expressions on the different terms, but it is something that is some operator applied to this element, and this element we are going to interpret it as a time derivative of a force, which is also a jerk. So it's just to say that all this model can be interpreted as, instead of modeling B, it's almost equivalent to model J here, and we will have some models that do that. Just
so the parameter K is used in some sort of regularizing fashion, right?
Exactly. So, KV. So K is a kernel operator, and so we have K inverse inverse. So this is the regularization. This is where, for example, this justify this term help us prove all our existence theorems, for example, and show that all our optimal control problem are at least well defined, that the control exists. I mean, you can given a control, you can solve the control equation at every time, for example. So we so this is what we did in a paper with Dainissier and Nicolas Charon and Sylvain Aguillère, in which we defined still a geodesic model, but in which now, instead of estimating the optimal growth tensor, linearized growth tensor, we were estimating an optimal Yank for different cost function, and we also proved nice properties for this model. This is okay. I don't think I have too much time to give the details, but this shows that when we when we have a very simple model in which the growth is restricted to be a constant depending on x times the identity matrix, so the growth is mostly scalar. The this Yank here that we have is simply the gradient up to a multiplicative constant, the gradient of this scalar growth. So it gives a connection between the two approaches in this special case. So just to conclude, I just want to mention that we have other models in which, so the previous model were essentially optimizing growth combined with elasticity so that we get a transform. We're able to transform a shape into another one. More realistic models would model growth independently from the shape motion and let the shape motion find its own trajectory by essentially trying to find the optimal transformation with a given growth. And so now you have an extra term in the model that tells how growth occurs. And of course, growth can occur in a way that depends on the shape that is evolving, and so we have different processes that are happening together and are interconnected. I just want to cite, for example, an approach that was going that way with that by a paper by Bressan and Levica that were modeling that using pure elasticity. When you do that, they were able to prove very nice theorem and do very nice mathematics, but at the end, you only have solutions of this growth model on bounded intervals. You cannot prove that your solution has your model has solution in arbitrary time. Of course, if you cheat and you add our regularization that we have with this KV inverse or this norm in V, you can prove that, and you get models that are similar, a little more complex than those that introduced by Bressan and Levica, but that allow for existence of solution in arbitrary time. We also have a way to generate growth in through a reaction diffusion convection equation for which we are able to prove existence theorem. So we get a system that looks like this. What is important is that there is a term that defines the motion as a function of the Eulerian velocity, then a term that defines the Eulerian velocity as the function of something that relates to growth, and then with this P related to growth and some evolution of the growth that depends on phi and on V also. So we get these couple equations and we were able to prove once again as part of Danny's dissertation that these equations have solution in arbitrary times, which means that we can use this equation to define. So this is just showing some growth happening to define optimal control problems in shapes trying to optimize growth. Well, actually, we were not trying to optimize growth, but trying to find, for example, what is the given an observed evolution, what was the most likely place where the growth has started, what was maybe the source of a disease. But this just to mention, going back to this is our more recent work on that, probably our more advanced model, for which we have obtained these results, and some results related to optimality of the existence of optimal solution of optimal control problems with this type of models, but this is still fairly open on how to solve this optimal control problem and whether the solutions that are found are relevant for application we're interested in. For example, one of them maybe related to this is to, given some evolution of atrophy, maybe rather than growth, understand what was the source, where exactly a disease that creates atrophy has started. Okay, I'm stopping here, and thank you for still listening.
Well, thanks a lot for the great presentation, Dr. Younes. So we have the possibility to for questions. I have some. Maybe I can start. So the first question is so the beta omega. So is that one of the causes of the loss? Yeah, that for example that system works, right?
Mm-hmm.
So I'm guessing that is some sort of source of problems, in the sense that it might cause some loss of regularities.
Yeah.
But you can play with diffeomorphisms a little bit, right? So to put yourself in the most optimal conditions. I don't know how to call them. I think I've seen in some geometric flows paper or something like that. It's called something trick. Now I can't remember. In which you use the optimal. You play with the parameterization so that you put yourself in a setting in which there is no degeneracy anymore.
Oh, yeah. With when you do this exponential transformation, something like that.
Something like that.
And it's yeah. No, but it just goes as far as allowing you to prove short. I mean, we're using that by the in the paper, but it goes as far as allowing you to prove short-term existence, not long-term existence of solutions. And I mean, it's the if you have I mean, I'm trying to remember exactly how we use that trick, but it's it shows that, I mean, it allows to control some of the norms of some of the I mean, it for example, we use it and I mean we try to write this as an ODE in infinite dimensional space, and we prove that the right hand term of the ODE in that case is Lipschitz, and we need to use these tricks to do that. But then you have always the fact that an ODE can explode in finite time, and this we cannot avoid unless we, at least in our computations, unless we add this regularization with this KV inverse in this equation.
Thanks. Other questions? Well, I can keep going in time. So the other thing that I have in mind is that most of the results that you're showing us are in species with high regularity. So namely, you have smooth curves, smooth CP, for example, something like that, right?
Mm-hmm.
So would there be any advantage to put yourself in some low regularity frameworks? So let's say that you have some, growth which are kind of either instantaneous or just irregular or something like that. Would that be of any help doing that? For example, trying to reformulate everything into an optimal transport problem or something like that, like something which you can allow for low regular type of transformations.
So you are speaking, I mean, for the I'm trying to find an application first. Before I even I don't know how to do what you suggested, but maybe you have a better idea. But in terms of applications, I at least in medical imaging, I don't see any situation in which you have non-regular growth. For example, I mean, we're applying that mostly to atrophy, or we want to apply that mostly to atrophy in the brain. And this is really, I mean, the real difficulty here is that the changes are very, very very small, but I don't think they are not smooth. I mean that, but at least there is no evidence of that. There's not a very deep hole that is created in the brain when you have some neurodegenerative disease. So I don't know. I mean, there may be situations in which growth has to be modeled in creating non-smooth transformations, but I'm not sure. I mean, never thought about it actually. So maybe it's the best answer. But all these methods, if you remove smoothness, they don't work. I mean, you have to find new approaches to study these models. On the other hand, optimal transport methods in this context, they don't give great transformations.
Right.
So there probably are two different situations that you want to consider.
Right. Other questions? It is thanking you. Right. Well, if there are no other questions, let's thank Dr. Younes again for the great talk. It was great to have you here in the seminar series. Thanks a lot.
Thank you. Thank you for inviting me. Thanks.
Oh, I get the pleasure. I get the pleasure. All right.